If you were to stand here for a billion years, you would see the mountains crumble to dust. You would see the oceans boil away or freeze into ice. You would see the stars above your head burn through their fuel, flicker, and die. From our human perspective, the universe feels solid. It feels permanent. We wake up, we drink our coffee. We go to work. We live our lives on a stage that seems built of bedrock. We assume that a rock is a rock, that a planet is a planet, and that the past is a locked door that can never be reopened. But if we were to zoom in, if we were to peel back the skin of reality and look at the machinery beneath, that sense of permanence would vanish. There is a rule at the heart of the universe that defies everything we know about common sense. It is a rule that says matter is not solid, but a ghost. It says that an object does not have to be in one place at one time, but can be in many places at once. And perhaps most disturbingly, it suggests that, at the deepest level, the universe does not have a single history. It has every history. This is the story of quantum mechanics. It is the most successful theory in the history of science. It predicts the behavior of the sun, the stability of the ground beneath your feet, and the very chemistry of life itself. But to accept it, we have to let go of our intuition. We have to accept that the universe, at its most fundamental level, is far weirder, far more chaotic, and far more wonderful than we ever dared to imagine.
I think it's important to say that there aren't different rules of the game in the subatomic world and the world that we observe, this world of common sense, let's say, that we perceive. And it's pretty well understood, I would say it's well understood, how the world that we see emerges from this rather strange but well-defined behavior that we see in the subatomic world. And it's not only the subatomic world, by the way. We have an increasing number of quantum technologies that are really based on this behavior, the quantum computers being a good example. And so you see that this is not just something that you can say, well, we don't need to think about it really because it's in the world of atoms, because we're using that behavior now in technologies. And so it really does become an important theory to try to understand.
The death of the clockwork. For over 200 years, science was dominated by a single, beautiful idea. It was the idea of the clockwork universe. This was the vision of Sir Isaac Newton. In Newton's world, the laws of nature were absolute. If you knew the position of every particle in the universe, and you knew the speed at which they were moving, you could, in theory, predict the future with absolute precision. The universe was a machine. It was deterministic, cause followed effect in an unbroken chain. If you threw a ball, its path was set the moment it left your hand. It didn't have a choice. It didn't have a probability of going somewhere else. It followed the rails of gravity and motion. This view gave us a sense of control. It meant that reality was objective. It meant that the moon was there, orbiting the Earth, whether we were looking at it or not. But in the early 20th century, as we began to build better machines, we started to look closer. We looked at the atom. And as we peered into that microscopic world, the machine broke. We found that the subatomic world is not made of hard, billiard ball particles bouncing off each other. It is made of something much more elusive. We found that the predictability of Newton was an illusion. The pioneers of this new physics, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, realized that down in the basement of reality, the lights are off and nothing is exactly where it seems to be. The particle that takes every path. To understand this, we have to revisit an experiment that has puzzled physicists for 100 years, the double slit. Imagine you have a light source and a screen. In between, there is a barrier with two small slits cut into it. If you were to fire sand, tiny grains of matter at the barrier, most would bounce off. Some would go through the left slit, some through the right, On the back screen, you would get two piles of sand, two bands. This is how particles behave. They travel in straight lines, but if you fire electrons, the building blocks of matter, something breathtaking happens. If you fire them one by one, watching them land on the screen, a pattern emerges. It isn't two bands. It is a series of alternating bright and dark stripes. This is an interference pattern. It is the signature of a wave. It is what happens when two ripples in a pond overlap where the peaks meet, the water gets higher. Where a peak meets a trough, it goes flat. But we didn't fire a wave. We fired a single electron, a single chunk of matter. How can one particle create a wave pattern? Who is it interfering with? The standard answer is that the electron goes through both slits at once. It splits, interferes with itself, and then recombines. But there is a deeper, more profound way to think about this. It was proposed by the American genius Richard Feynman. Feynman called it the sum over histories. He suggested that when a particle travels from point A to point B, it doesn't take a single path. It takes every possible path. It goes through the left slit. It goes through the right slit. But it also takes a path where it loops around the room. It takes a path where it flies to the moon and back. It takes a path where it goes to the edge of the universe and returns. The particle explores the entire geometry of space-time. Most of these crazy paths cancel each other out. The path to the moon is canceled by a slightly different path to the moon. But the paths through the slits reinforce each other. They add up. And what we see, the reality that appears on the screen, is the sum of all those infinite histories interacting. This implies something staggering. It implies that the solid reality we see is just the most likely outcome of an infinite number of ghostly possibilities. The illusion of touch. Now you might say, well, that's fine for electrons, they are tiny. But I am big, I am solid. This rock is solid. Is it? Let's look at the atom again. We are taught in school that an atom is a nucleus surrounded by electrons orbiting like planets. That is a useful model, but it is wrong. If we were to take an atom and blow it up to the size of a football stadium, the nucleus, the hard, heavy part in the middle, would be a marble sitting on the center spot. So, where are the electrons? The electrons are tiny, invisible specks buzzing around the very highest seats in the stands. Everything in between the pitch, the lower stands, the car park is empty space. And since you are made of atoms, you are almost entirely empty space. If we could squeeze all the empty space out of the entire human race, all 8 billion of us, we would fit inside the volume of a single sugar cube. So why don't you fall through the floor? Why can I hold this rock? Why does it feel hard? You are not feeling matter. You are feeling a force. There is a rule in quantum mechanics called the Pauli exclusion principle. It states that two electrons cannot occupy the same quantum state in the same place. They are territorial. They refuse to overlap. When my hand pushes against this rock, the electrons in my skin and the electrons in the rock are pushing back against each other. Not because they are touching. They never touch. But because the laws of the universe forbid them from being in the same space. What you interpret as touch is actually the electromagnetic force, repelling you. You are hovering. You are floating on a cushion of quantum rules, nanometers above the chair you are sitting on, never actually making contact with the world around you. This force, this degeneracy pressure, is so strong that it is what holds up the stars. When a star dies and collapses, it is this same exclusion principle that stops it from shrinking forever, creating a white dwarf. The only thing keeping a dead star from collapsing into a black hole is the refusal of electrons to be in the same place. The star in your kitchen. This quantum weirdness isn't just about empty space. It is the reason we are here at all. Consider the sun. It is a giant ball of hydrogen gas For a star to shine, it needs to fuse protons together to make helium. This releases the energy that warms our planet. But there is a problem. Protons are positively charged, and as we know from magnets, like charges repel. If you try to push two protons together, they push back. The closer you get, the harder they push. This is the Coulomb barrier. According to classical physics, according to Newton, the sun is not hot enough to overcome this barrier. The protons are moving fast, but not fast enough. They should bounce off each other. The sun should not ignite, so why is the sun shining? Because of quantum tunneling. Remember, a particle is not a hard ball. It is a wave of probability. Its position is smeared out. While the proton is mostly on this side of the barrier, there is a tiny, vanishingly small probability that it is already on the other side. Occasionally, very rarely, a proton in the core of the sun will simply appear inside another proton. It cheats. It tunnels through the wall that it shouldn't be able to cross. Because there are so many protons in the sun, this rare event happens enough to keep the fusion reaction going. The light hitting your face right now, the energy that drives the weather, the crops, and life itself, is a direct result of particles walking through walls. You are bathed in the glow of quantum weirdness every single day. The arrow of time. But there is a deeper mystery here. A mystery that connects the quantum world to the end of the universe. If I show you a video of a planet orbiting a star, and I play it backward, it looks perfectly normal. The laws of physics work just as well forward as backward. In the quantum world, time is symmetric, but in our world, time has a direction. We see eggs break, but we never see them unbreak. We see sandcastles wash away, but we never see the ocean build them. This is the arrow of time, and it is driven by something called entropy. Entropy is a measure of disorder. It is a measure of how many ways you can rearrange the components of a system without changing its appearance. There is only one way to build a perfect sandcastle, but there are infinite ways to have a pile of sand. So, as the universe evolves, it naturally moves from order to disorder, from the unlikely to the likely. What does this have to do with quantum mechanics? Everything. Because the universe started in a state of incredibly low entropy. It was highly ordered. Over the last 13.8 billion years, that order has been decaying. Stars are engines of entropy. They take ordered hydrogen and burn it into disordered heat and light. We are living through a brief, brilliant flash of structure in a universe that is slowly winding down, and quantum mechanics is the engine driving that change. Spooky action. Before we get to the end of the universe, we have to deal with the problem of space. Albert Einstein famously hated a specific prediction of quantum mechanics. He called it spooky action at a distance. The theory predicts that two particles can become entangled. They lose their individual identities and become part of a single mathematical object. If one spins up, the other must spin down. They are perfectly correlated. Now imagine we take these two particles. We leave one here on Earth, and we take the other to the Andromeda Galaxy, 2.5 million light-years away. According to the rules of superposition, until we look, neither particle has decided which way to spin. They are both in a cloud of probability. But the moment I measure the particle here on Earth, let's say it snaps into the up state. The particle in Andromeda instantly snaps into the down state. How did it know? It is 2.5 million light-years away. Even light would take 2.5 million years to get there. But the connection is instantaneous. Einstein argued that this was impossible. He said it broke the speed limit of the universe. He spent years trying to prove that the particles must have had secret instructions hidden inside them all along. But he was wrong. We have done the experiments. We have measured photons separated by vast distances. The spooky action is real. This tells us something profound about space. It tells us that distance might be an illusion. It implies that, at a fundamental level, the universe is much more interconnected than it appears. Two things can be separated by a galaxy, and yet, in the eyes of quantum mechanics, they are standing right next to each other. The measurement problem. This brings us to the most controversial question in physics, the question that keeps physicists awake at night. We have established that before we look, particles are waves. They are everywhere at once. But when we look, they snap into focus. The wave collapses. Why? What is special about measurement? Does the universe require a conscious observer? Does it need a human mind to make it real? In the 1930s, Erwin Schrödinger designed a thought experiment to show how absurd this is. He imagined a cat in a box with a poison triggered by a quantum event. If the atom is in a superposition of decayed and not decayed, then the cat must be in a superposition of dead and alive. But when we open the box, we never see a blurry, half-dead ghost cat. We see a living cat, or a dead one. At what point did the universe decide? This is the measurement problem, and for decades we simply ignored it. We said, shut up and calculate. The math works, so don't ask why. But recently, a new generation of physicists is taking a radical idea very seriously. The many worlds in the 1950s, a graduate student named Hugh Everett asked a simple question. What if the wave never collapses? What if the particle doesn't choose one path? What if it continues to take all of them? This leads to the many worlds interpretation. It suggests that, when you measure the electron, the universe splits. In one branch of reality, you see the electron here. In another branch, which is just as real, just as physical, and just as solid a version of you sees the electron there. This implies that reality is branching constantly. Billions of times a second, with every quantum interaction, new universes are born. There is a universe where the asteroid missed the Earth and the dinosaurs are still here. There is a universe where you didn't watch this video. There is a universe where you made that choice you regret, and a universe where you didn't. In this view, you are not a single isolated individual. You are a multiplicity. You are a vast, multifaceted object spread across infinite dimensions. You are a choir of infinite variations, living out every possible life across the branches of the multiverse. We cannot communicate with these other branches. To us, they are gone forever. But the math suggests they are there. The heat death. This brings us back to the arrow of time. If the universe is constantly branching and entropy is constantly increasing, where is it all going? What is the final fate of this quantum reality? Eventually, the stars will burn out. The galaxies will drift apart. Even the black holes will evaporate, leaking their energy back into the void through a quantum process called Hawking radiation. The universe will become vast, cold, and empty. There will be no light, no life, just a thin soup of particles floating in the dark. This is the heat death of the universe. It is a state of maximum entropy. It is a state where nothing interesting can ever happen again, because everything is the same temperature. The arrow of time will cease to exist, because there is no way to distinguish the past from the future. It sounds depressing. It sounds like a tragedy, but I don't see it that way, because we are here now. We are living in the stelliferous era, the era of stars. We are living in that brief, golden moment between the Big Bang and the eternal dark. We are made of atoms that were forged in the hearts of dying stars. We are clumps of matter that have become complex enough to think, to feel, and to ask questions. We are the universe, waking up and looking at itself. Quantum mechanics tells us that our existence is improbable. It tells us that we are balanced on a knife edge of probability, surviving only because of the specific rules of tunneling and exclusion. It tells us that reality is not a fixed, boring stage, but a dynamic, shimmering ocean of possibility. The fact that we are here to see it, the fact that we can stand on this rock, look up at the sky, and understand the equations that govern the stars, that is the true miracle. So, the next time you look at a light bulb, remember the quantum jumps creating that light. The next time you touch the hand of someone you love, remember the exclusion principle that allows you to feel them. And remember that in a universe of infinite possibilities, you are the one that became real. Thank you for exploring the universe with us. If you want more videos like this, click here for our next documentary. And remember to subscribe to join us in the next reality.